Hello everyone, welcome to COMP382 Languages, Machines and Computation. So in this video we are going to talk about properties of regular languages and we are going to focus on closure properties. So far our main discussion in this course was regular languages. Regular languages is a class of languages, the set of languages that has some specific properties. Regular languages was the smallest and the simplest class of languages in the hierarchy of Chomsky. Remember, we had a hierarchy like this that so let me actually use a different pen type. We had a hierarchy like this, that we had a set of languages that we call it regular, and then we had another set of languages which was a superset of this. This was context-free languages that we are going to talk about it after the midterm. And after that we had another set of languages that was represented using Turing machine, and outside of that all of those problems which are not decidable and so on. Okay, so far we have actually focused on regular languages, this class of languages. This is a set of languages that all of them are going to have specific properties. So in this video I'm going to talk about these properties. In general, the properties that we define for a class of languages can be divided into two different sets of properties: decision properties and closure properties. So decision properties for a class of language is going to be asking about some questions that the answer for them is yes, no, and we try to actually check if we can find an algorithm that you pass it a language and your algorithm answers, for example, some specific property holds for this language or not. We will actually cover this discussion in a separate video, so I'm going to skip it for now. The main set of properties that I'm going to focus here is going to be closure properties. So closure properties are in fact is focused on some operations that we define over the languages. And so basically for a class of languages, for example, for the class of regular languages, we are interested to know that if I apply a couple of operators, for example, union, intersection, I will actually listed all of these operators, that if you apply this operator over one or two language, the result, which is going to be another language, is going to be again in the same class of language or not. So let me actually just this is the main definition of the closure properties. So we are going to check that the closure property for regular languages over this set of operators. So I'm going to check that, for example, if I apply union operator over two languages, the result, which is going to be another language, is going to be in the class of regular languages or not. If it is in the class of regular languages, we say that okay, regular languages are closed under this specific operator. For example, regular languages are closed under union. They are closed under intersection. So if I have two regular languages, if I get the intersection between them, the result is going to be another language that is going to be again a regular language. So I'm going to discuss all of these operators: union, intersection, complement, difference. You can see that all of these operators are going to be operators applied over the sets. Each language is a set, so all of them are applicable. Then I will actually explain what is reversal operator, what is closure operator, concatenation, homomorphism, and inverse homomorphism. And actually, interestingly, we will see that regular languages, the class of regular languages, are closed under all of these operators. So as the regular languages are going to be very simple, the simplest class of languages that we discuss in computer science, in the context of computer science, they are going to be closed under all of these operators. If you applied any of these operators over two regular languages, over one regular language, the result is going to be again a regular language. So let me actually just explain about these closure properties. But at the end, we will see that the main purpose of discussing all of these closure properties is to just getting a better understanding of this class of languages. So, for example, if I am interested to know that if a specific language is regular or not, and it's not going to be that easy, but then I will understand that, okay, this is going to be created by the union of two other languages that I know those two other languages are regular. So I can conclude that this language is also a regular language as well. So I will actually post a document that will give you some example of where we are going to use these closure properties. So let's just skip these explanations and jump into these operators, and I'm going to actually prove to you that regular languages are going to be closed under all of these operators. The first operator that we are going to discuss here is going to be the union operator. So we have already actually defined the union operator when we discussed about regular expressions, remember? So the definition of the operator is exactly the same. And the theorem that, the proposition that I'm going to prove here is that regular languages are closed under union, which means that if I have two languages, like let's call them L and M, that I know both of these languages are going to be regular, then I can prove that the union of L and M is going to be regular as well. Okay, so how can I prove it? The proof is going to be very simple. The thing is, if L is regular, it is possible to represent L in a form of a regular expression, right? So let's just assume that the regular expression that I can write for L is R. If M is a regular language, then it is possible to write it down in a form of a regular expression. Let's just call that regular expression S. So the union of L and M is going to be a set of strings that either it is in L or it is in M. I can create a regular expression that represents this set of languages, this set of strings, sorry. And I can actually use the union operator between the regular expression R and regular expression S. So in this way, I have created another regular expression that basically is going to represent all the strings in this language, the union of L and M. And actually, that's going to be a proof, a valid proof. This is a formal proof. And we prove that regular languages are closed under union. The next operator that we are going to talk about is complement. So if I have a language, what is going to be the complement of the language? A language will be defined over an alphabet, right? So if I have a language L over the alphabet sigma, the fact is L is going to be a subset of sigma star, right? The subset of all strings that you can define over this alphabet. So the complement of L that we represent it usually in this way, we put in a bar over L, is going to be defined as just like the way that we define complement over the sets in the set theory. Okay, so all of the strings which are in sigma star, but they are not in L. So you can actually define it in this way. All the strings which are in sigma star, all strings that you can define over this alphabet, which are not in the language L. Okay, so this is going to be the set of the complement of L. Now the thing is, I wanted to prove that regular languages are closed on their complement. So which means that if L is regular, then the complement of L is also regular. So how can I prove this? I mean, the way that I'm going to actually prove it again is a constructive proof. I will show you that if I have a regular language L, so I should be able to represent it as a DFA, right? So there should be a DFA, deterministic finite state machine for L. I wanted to show you that from that DFA I can create another DFA, another finite states that represent the complement of L. And this is actually the way that I can create that DFA. So assume that this is a DFA, this is a general DFA that we define for a regular language L. Okay, so I can create another DFA that represent all the strings in complement of L. So think about it in this way. If I have a DFA for L, if I pass any string from the valid alphabet, that string is going, if you pass it to this DFA, it is going to end up in one of the states in this DFA, right? So if you start from the starting state, if you pass W, if you start from the starting state, if you pass W, you will end up to another state. So another state in this DFA. It doesn't matter which one. You will end up to one of these states. So it can be a final state or a non-final state, right? So if Q is a final state, which means that the string W will be a part of the language. If Q is not in the set of final states, then W is not going to be in L, which means that W will be a part of the complement of L, right? So as simple as that. So all those states which are final in the DFA, in the original DFA, in the new DFA that I'm going to create for L bar, I will mark them as non-final states. So here it is. I have actually marked all those final states as non-final, and I will mark all of those states which are which are non-final states here, for example, this one or this one, I will mark all of them as final states. So in this way, in this new DFA that I have created here, if the strings end up to one of these states which were non-final in the previous, in the original DFA, it will be accepted, which means that it is going to be a part of the complement. And if it will be end up to an accepting state in the original DFA, it will end up to a non-final state in the new DFA. So that's it. I can actually just prove that this DFA really represent the complement of L, and this is enough to prove that the regular languages are closed on their complement. So the next actual operator that I'm going to discuss is intersection. So we are going to prove that regular languages are closed on their intersection. If I have two languages, L and M, which both of them are regular, the intersection of these two languages are going to be a regular language as well. How can I prove this? In terms of just mathematically, I can prove this easily using, these two facts that I know that regular languages are closed on their union and they are closed on their complement. So using the De Morgan laws, I can easily actually show that, okay, the intersection of these two sets is going to be actually equal to the complement of union of the complement of each one. So this is just applying the De Morgan laws a couple of times. So if I have L, I can create the complement of L, which is going to be regular. I can create the complement of M, which is also regular, then get the union of them, and then again apply the complement. So definitely the result is going to be a regular language. This is enough to prove it, but I'm going to also show you a constructive proof which is going to be very useful, that if I have two languages, L and M, that both of them are regular, which means that I can create a finite state for this one and I can create a finite state for this one. I'm going to show you how we can create a finite state for the intersection of these two languages. So just assume that I have created a DFA for L, a DFA for the language M. Okay, so this DFA is going to have a set of states, the alphabet, and one starting states here, a set of final states, and the transition function. The same actually for the other language M. So I can create a deterministic, one thing here is that if you are getting an intersection between two languages, definitely the alphabet is going to be the same, right? Because if the alphabet is not the same, of course the intersection of these two set of strings is going to be empty. Okay, so it's not possible to have a string that belongs to both of these, except actually epsilon, which is if the intersection is epsilon, you can actually just represent it as a using a finite state. So the example, this algorithm that I'm going to show you here is going to focus on this fact that the alphabet is the same. Okay, so I can create another DFA for the intersection of L and M, and the whole idea of this algorithm is that I'm going to try to create a DFA that simulates running a string over L and M simultaneously. So it's just like if I have a string like W, if I pass it to the DFA for the language L, and if I pass it to the DFA for the language M, simultaneously actually just follow that what would happen to strings in these two DFAs, and I'm going to actually just represent it using another DFA. So the result is going to be another DFA that the set of states in this DFA is going to be a Cartesian product of all the states in the first DFA and all the states in the second DFA. Here the order is not really important. It doesn't matter which one is going to put first, but just know that they are going to be each set is going to be a pair of states, that one of them is coming from the first DFA, the other one is coming from the second DFA. So every state is going to be a pair of states. P is from the first DFA, Q is from the second DFA. Okay, so the starting state is going to be that pair that the first the starting state of the first DFA, you have the starting state of the first DFA and the starting state of the second DFA. The final states are going to be those pairs that both of the states are going to be final states, one of them in the first DFA, the other one in the second DFA. And I'm going to show you that how we can define the transition functions. So let me actually show it to you. I have the explanation written here, but let me show you it to you this graphically here. Just assume that you have a deterministic finite state here and a deterministic finite state for the other language here, right? So I am going to create another a new deterministic finite state for the union of these two languages. Here the starting state in the new DFA is going to be a pair of, for example, if Q0 and P0. So the state is going to be marked as Q0, P0. Then you will have, for example, if I have K number of states here and P number of states here, the total number of states in the DFA for the intersection is going to be K multiplied by P number of states, okay? So you need to have all of those states, and then the final, okay, let me actually just show you the transitions. So, for example, from Q0, P0, where you are going for each transition that you are going to add, it's just like, for example, for the transition over, a symbol, for example, like A. You would check where in this final states you are going over A. If you are going to, for example, a state like Q1, and then you also double check that where you are going with the transition A in this finite states. Let's just call it P1. Then in the new DFA that you are creating from Q0, P0, you will go with the transition A, you will go to Q1, P1. Okay, so this is the way that we actually execute the transition. So in general, between all of these set of states, for example, if you have a states like Pi, another states here Qi, so you should have a states Qi Pi, right? This is going to be that pair. And the transitions for this one is going to be defined as the transition, for example, over A is going to be going to the states Qj and Pj here. Okay, so I think it's now clear that how you are going to put all of these transitions between the sets. And at the end, all those states that both states in this, or both states in the pair are going to be final states, they are going to be marked as final state in the final DFA. The thing is, you are looking for the intersection of the strings, right? Intersection of two languages. So you want the string to be accepted here and to be accepted here. That's why both of these two states in the pair should be accepting states in their corresponding DFAs. Let me actually show you an example here. For example, if you have two languages like the language of binary strings with even number of zeros, the language of binary strings with the pattern this, and you wanted to actually create a deterministic finite states for the intersection of these two languages, which will be the language of all strings, which has even number of zeros, and it also actually includes this pattern. You can do it using actually, in this way that I showed you, create a DFA for this language, create a DFA for this one, and then create the intersection of these two deterministic finite states. If you create a finite state for the language, it's going to be easier in this example, but just do it as an example for yourself. Okay, the next operator that I'm going to cover is set difference. So again, each language is going to be a set of strings, right? So I can define this operator, the set difference, over the regular languages as well. The theorem here is that I have two languages, L and M. I wanted to prove that if L and M, both of them are regular, L minus M is also regular, or M minus L is also regular. And I can prove it using, again, this actually rule over the sets, that I know that L minus M can be written as the intersection between L and the complement of M. So yes, because the regular languages are closed on their complement, M complement of M is going to be regular as well. And I just actually discussed that how we can create a DFA for the intersection of two regular languages. So that's it. That's enough to prove that regular languages are closed on their set difference. The next operator that I'm going to discuss is the reversal operator. So let me actually first define what does this operator do. If I have a string like W defined over the alphabet sigma, the reverse of this string is going to be another string that it's just like you are reading W from right to left. Okay, and we basically just show it as WR. So if W is defined as 0, 0, 1, 1, 1, the reverse of W will be 1, 1, 1, 0, 0. So it's just like you mirror it. You read it from, instead of left to right, you read it from right to left. So we can define the reversal operator over the languages as well. So if L is a language over the alphabet sigma, we represent the LR to be the set of all strings in L, all strings that the reverse of them are in L. So basically, if the string is in L, if you reverse it, the set of all these strings are going to be in LR. Okay, so now we wanted to actually prove that regular languages are closed on their reversal operator. So if you have a regular language, if you reverse all the strings in the language, the result is going to be a regular language. And again, the proof that here I'm going to show you is going to be a constructive proof. I'm going to show you that if you have a regular language, it means that you can create a deterministic finite state for your language, right? I am going to show you how to create a finite state for the reverse of L. So in that way, the reverse of L is going to be regular as well. So just assume that this is the DFA. You can see that this is a very general actually graph. So you have a DFA for L. I am going to create a finite state for the reverse of L. And basically this is going to be actually an epsilon NFA, I mean at the end the result, but it doesn't really matter. You know that if you can create an epsilon NFA for a language, you can create a DFA for that, and basically it just means that you have a regular language. So again, here the idea is that if you have a language, a string W, which is a part of the language L, it means that if you start from Q0 and if you read W, you will end up to one of the final states, right? So if L is a part of, if W is a part of L, I wanted to create a finite state that for all strings W, WR is going to be a part of this new language that I have created, right? So in my new finite states, WR should be accepted. So if W is in the language, WR, so it's just like WR will start from the end of the W, right? So every strings that you start from here and end up here, I wanted to basically just start from one of the final states, and if I reverse all the transition, I end up here. So the whole action that I will do is I will start reading the strings from the final states, and will reverse all of the transitions in the graph. And then I actually just wanted to check that all those strings, that if I start from one of the final states, I will end up to the starting states. So all of these actions are going to be something like this, that I want all of the final states to be a starting state. I want to reverse all the transitions, and then I wanted to actually mark the starting state as the final state. So the thing is, because I cannot have multiple starting state, to just fix this, I will add a new starting state, and I will add some epsilon transition from this new starting state to all of the original final states that here they are not marked as final. So they are all marked as, it's just like all of them are going to be some starting state for me, so they are not final state anymore. And the starting state will be marked as a final state now. Okay, so it's exactly just like you are simulating starting from one of the final states and end up to the starting state with this fact that every transition has been reversed. So it's just like you started from the end and you go back to the beginning. So now I have a question for you. So I mentioned that all the final states are going to be marked as non-final, and the starting states will be marked as a final state. What would happen if in the original DFA Q0 was a final state? So what would happen in that case? Should I actually mark as Q0 as a non-final state or not? And so basically the answer is yes, the Q0 will be still a final state. Q0 should be the final state. It doesn't matter if it was final or non-final in the original DFA. And basically if Q0 was final, it basically just means that epsilon was a part of L. So of course epsilon will be a part of the reverse of L as well. So you should keep Q0 as a final state. Q0 will be actually the only final state in this new DFA. Okay, here again is an example that shows that, for example, if you have a if you have a regular language like this, that all the binary strings that if whenever you see a 1, it is followed by 2 zeros. I can create a finite state for the reverse of this, which basically means that for every every double zero that you will see, there should be a 1 after that. So if you think about that language, that's going to be a little bit difficult to create a DFA for. That's not very clear how to create the DFA for that. What you can do is just create a DFA for this language, then reverse it. So this is an example that actually the Q0 is going to be a final state. So you would just reverse all the transition, marked all the final states as non-final, and then marked the added a new starting states, and which basically, because here I only have one final state, I didn't really need to add this one, but just to follow the rules that I explained, I have just added. And at the end, mark the original starting state as a final state. So this one needs to be marked as a final state. And this is going to be a DFA for the reverse of this language. Not only that, if you have I can actually just prove it using a constructive proof over the regular expression as well. This one is also interesting because this just helps you to, if you have a language that you know how to create a regular expression for that, and you are interested in the reverse of that language, but that's going to be a little bit difficult to create a regular expression for the reverse of that, just create a regular expression for the language that you have, and then reverse that regular expression, and you will get a regular expression for the original language. And how to do that? This is the approach. If you for all the basis in the definition of regular expression that I have, remember in the regular expressions we define a recursive definition for that. We define some bases, and then we define some recursive parts for the definitions. The basis was epsilon is a regular expression, empty set is a regular expression, and all the symbols in the alphabet is a regular expression. So all of these bases, the reverse of this regular expression is going to be the same. So epsilon, if you reverse it, that's going to be epsilon. Empty is going to be empty, and each symbol A, if you reverse it, that's going to be the same. And if you have a general regular expression, let's just call it E, this will be created by applying one of the operators union, intersection, or clean closure between two other regular expressions, right? So for example, if E is the union of F1 and F2, the reverse of E will be created by getting the union over the reverse of F and then the reverse of F2. Okay, if E has been created by concatenation between two regular expressions f1 and f2, the reverse of E will be the reverse of f2 concatenated to the reverse of f1. Okay, and then if you have E as a that has been created by applying killing closure over another regular expression f1, so here you just need to reverse f1 and then apply the killing closure over that, so the result is going to be the reverse of that regular expression. Okay, so the next operator that I'm going to discuss here is homomorphism. This is actually a little bit different than the previous operators, kind of interesting. What is a homomorphism? A string homomorphism is in fact a function which applies, it's a function that will apply over a string, over the set of strings, and map it to another set of strings. So we will define it over a set of in fact, over an alphabet. Just assume that, for example, homomorphism will be applied over the alphabet sigma, and it actually mapped it to another set of strings. So this is going to be a function that will be applied over the alphabet sigma. So this is going to be a finite set of a finite set of symbols, and it will map it to a set of strings. Okay, so let me actually give an example. It actually makes it more clear that what does this mean, because the definition of the homomorphism is really important for us when we are discussing about the closure property. So just assume that we have the binary alphabet, and we have another alphabet that you can see that this alphabet, the alphabet in the range is can be different. It can be an alphabet the same as binary alphabet, or here I have defined it as the alphabet over two symbols A and B. So I can define a homomorphism which is going to be a function, let's just call it H over sigma, so that H will be applied over all the symbols in sigma and map them to a strings over this alphabet. So H0 has been defined as AB, H1 has been defined as epsilon. Okay, it's just one homomorphism, right? I could define another homomorphism, like let's just call it H prime. I could actually define another homomorphism that it actually maps 0 to A and maps, for example, 1 to A again. Okay, so this is also a valid homomorphism. Okay, or you can actually define another homomorphism in this way, that it actually, if you applied it over 0, it will be mapped to, for example, AA, and if you applied it over 1, it will be mapped to A. So this is just based on the definition that you define. So this is a valid homomorphism, this is a valid homomorphism. You just actually define it as a function that maps all the alphabet symbols in sigma to a string in another alphabet. Even that alphabet can be the same as sigma, but it just actually depends, it can be anything. So in this way, when I apply this homomorphism over a string, let's just assume that the string that I have is going to be defined over the alphabet sigma, right? So a string is going to be a string defined over the binary alphabet, for example, this alphabet. If I apply the homomorphism over this string, it's just like you applied it over all the tokens, all the symbols in this string, and then you concatenate them. So if I apply H over all the tokens here, it's just like you applied it over 1, you will get epsilon. So this is W, 1, 0, 1, 1, 0, right? You just applied H over all of them. So if you apply it over 1, it will be epsilon. If you apply it over 0, it will be AB. If you applied it over 1, it will be epsilon. If you apply it over 1, it will be epsilon. If you apply it over A, it will be AB. So the result is going to be AB, AB, right? Because all the epsilons are going to be gone when you concatenate them. So this is going to be the result. So this is the definition of the homomorphism. A homomorphism is a function. In fact, it's an operator. And the theorem that I'm interested here is that if I have a string homomorphism and if I have a regular language, if I apply this epsilon homomorphism over the regular language that I have, the result is going to be a language, right? A language in a different alphabet. It can be a language in a different alphabet. Now, I wanted to actually prove that that language is going to be a regular language as well. Okay, so how can we prove this? Basically, the idea is that if you have a language which is a regular language, you can create a deterministic finite state for that, right? I can actually show you that how to create a finite states for the homomorphism of the language. How? The thing is, if you have a homomorphism function, a string homomorphism, so basically that's going to be every symbol in the alphabet in your mapping is going to be, it's just like H will map every symbol here to a string in another alphabet, right? So in a string in this alphabet. Okay, so this is going to be a string here. So what you can do is that you can just keep the original DFA that you have, just replace every transition in the original DFA with, another, for example, you can create a DFA that represents this string. So basically this string is going to be a mapping. It's going to be a pattern, right? Because it is a finite set of tokens, you can just create a finite states for this one, right? And just replace that in this transition. So instead of having this transition with label A, you will replace it with, probably here they are going to actually have more number of states and just go from QI to QJ. All the final states are going to be the same. The starting state is going to be the same. Just the transitions will be changed. So it's just like if you have a DFA for L, you can create a DFA for the H of L as well. So the H of L can be a regular language, will be a regular language. So not only that, also I can actually show you that how to create a regular expression for your language. So if L is a regular language, it means that you can create a regular expression for that, right? If I define H as an homomorphism over L, I can show you that how to create a regular expression for H of L. So let me actually just show you an interesting example here. Just assume that you have a language that will be represented using this regular expression. This language has been defined over the binary alphabet, right? And let's just define a homomorphism that mapped 0 to AB and mapped 1 to epsilon. This is exactly the example that I showed you, here, right? This is exactly the same homomorphism here. I wanted to show you that if you have a language represented by this regular expression, just assume that this is your regular expression. If I wanted to see that what will be the regular expression for H of L, you can see that H of L will be defined over the new alphabet, which is A and B, and what is going to be that language and what is going to be the regular expression for that. It can be done easily in this way, that just create a regular expression for H of 0, create a regular expression for H of 1, here it is very simple. For the regular expression of h of 0, it's going to be AB is a valid regular expression, right? And epsilon is a valid regular expression. I just take these two regular expressions and replace them in this regular expression. So what I have as L is going to be 0, 1, sorry, let me just clean here, union L, sorry, 1, 0 star, right? I will replace 0 with AB and then replace 1 with epsilon, so epsilon, and apply the Killing closure over that, union, then replace 1 with epsilon, and then replace 0 with AB star. Okay, so this is the regular expression for h of L. So I can simplify this more. So if you simplify this regular expression, the first part is going to be AB, right? Union AB star. And here it's actually clear that I can actually simplify this as AB star, because it just actually tells you that all the strings, because basically this AB will be generated by AB as well, so getting the union here is not going to give you more, so I can just simplify it as AB star. So the result is AB star. So this is the regular expression for the h of L. So here I have one more question about the homomorphism. Just assume that L is not regular. Okay, can we say that h of L is also, if h is a string homomorphism, can we say that h of L is not regular as well? Is not, because L is not regular, h of L is not regular? The answer is no. If L is regular, definitely h of L is also regular. If L is not regular, I don't know if h of L is going to be a regular or a not regular actually language. And I can show it to you by just finding an example. We know that this language is not regular, right? This is, the first example that I showed you, this is not a regular language. We cannot create a finite states to represent this language. In the next video, I will basically give you another proof using pumping lemma to actually prove that this language is not a regular language. So just assume that we know this is not regular language, because we have already actually proved that this is not a regular language. And I have a homomorphism like this, H0, the homomorphism that maps 0 to A and map 1 to epsilon. This is a valid string homomorphism, right? If I apply this homomorphism over L, the result is going to be, you can see that the zeros will be mapped to A, ones will be mapped to epsilon. So it's going to be n number of A's and n number of epsilon. Sorry, n number of epsilon. So n number of epsilon, it doesn't matter that how many number of epsilons. If you concatenate any number of epsilons to a string, the result is going to be, it's just like n number of A, right? Where n is greater than or equal to 0. This is basically means that any number of zeros, right? I can represent this using this regular expression, just applying Killing closure over A. A star means all the strings that has any number of zeros. Sorry, any number of A's. So is this language not non-regular? Irregular? No, this language is regular, although L was not regular. So applying homomorphism over non-regular languages can simplify them to a regular language. So you cannot conclude that if a language is not regular, applying homomorphism over it make it a not regular or regular language. It is possible that it can actually make it a regular language. Okay, and the final actually operator over the languages that I'm going to discuss here is inverse homomorphism. And we actually are going to see that regular languages are closed over inverse homomorphism as well. But first, let's actually see that what is inverse homomorphism. So we know what is homomorphism, right? Okay, just keep that definition that we know what is string homomorphism. That is a function that maps an alphabet to a set of strings in another alphabet. Okay, so if I have a language L that has been defined over this alphabet, let's just define it over the alphabet phi here. I believe the pronunciation for this one is phi, but if I'm wrong, excuse me. So if L is a language defined over this alphabet, okay, I wanted to define the inverse homomorphism. So homomorphism is a function, inverse homomorphism is also a function, but this is just the inverse of the function. Okay, how we can define the inverse homomorphism over the language? The inverse homomorphism over the language just basically means that it just tries to reverse this mapping. H will map from alpha from sigma to phi, right? So inverse of that is going, if you apply the inverse of that over phi, it's just like you are looking for all the strings whose homomorphic image are in L. Okay, so you are interested in these strings here that if you applied H over them, they are appeared in L. Okay, so basically just the reverse of the homomorphism. But it might be actually, it actually looks simple with this definition, but in practice you might actually see some examples which are tricky. Let me show you some example here. Okay, assume that sigma is a binary alphabet and I have phi defined as AB. And again, that homomorphism that I have actually discussed before, that mapped 0 to AB and 1 to epsilon. Okay, so now let's just actually see that what is going to be the result if I apply inverse of this homomorphism over AB. Remember, previously we applied H over 0 and it maps 0 to AB, right? It maps 1 to epsilon. Now I'm going to just reverse it so that I can apply the reverse of H over the strings that have been defined over this alphabet, and the result is going to be a string defined over sigma. Okay, so let's just see that, for example, if I apply reverse of this homomorphic function, homomorphism, over AB, what's going to be the result? Based on this mapping, if you apply the reverse of that over the string like AB, the result is going to be 0, right? How about if I apply the reverse of this homomorphism over A? Over a string which is A. You can see that A is a valid string over this alphabet. What will be the result? If I look at the definition of the homomorphism here, I can see that with this definition, the homomorphism, this function, is not going to always a single A. So if you see a single A, it just means that the inverse of this homomorphism will not map it to anything in the sigma. Okay, so it just actually tells you that the strings whose homomorphic image are in L. So if a string is, I just wanted to try to actually tell you that some of the strings don't have the inverse homomorphism. Some of the strings here cannot be mapped and back here. Okay, some of them will be actually cannot be mapped. So this is one of those examples. If you have a single A, it is not possible to get it with applying H over any binary string. Okay, if you apply H over any binary string, it's not possible to get A. So it's just simply, you just define it as not defined. So sum of the strings over phi cannot be mapped back to sigma, just like, for example, this string. Because basically the homomorphism has been defined over this one, but the inverse homomorphism hasn't been defined for some of the strings. So with this fact, let me actually give you another example. So if I have a language like L that has only two strings, this string and this string, what is going to be the result of applying the reverse of this homomorphism over L? Okay, so this is a string, has been defined over phi. It only has two this is a language, has been defined over phi. It only has two strings. I just wanted to see that if I look back at the binary alphabet, if I apply the reverse of this homomorphism, what's going to be the result? Let me actually do it one by one. So if I look at this string B A B A, if I wanted to apply this homomorphism, the reverse of this homomorphism, is it possible to find any binary strings is it possible to find any binary string belongs to sigma star that if I apply H over that, the result will be BABA? If it is, so the result of applying the reverse of this homomorphism will be W. So I'm looking for this W. But if you look at H, you will see that it's not possible to get BABA if I apply this homomorphism over any binary string. It is not possible. So basically this string cannot be converted back. So there is no language, there is no string in the set of all binary strings that represent this one. So it's just like this one will be removed. We don't have any image for this one in the binary strings. How about this one? This one, if I actually look back at these, so this one will be undefined, but how about the other actual case? How about AB, 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 AB? I'm looking for all those strings that if all those binary strings that if I apply homomorphism over them, the result will be AB, AB. Okay, I know that H of 0 will generate AB for me, right? So AB, AB will be basically double 0. So, if W is equal to double 0, when you apply H over that, the result is going to be AB, AB. Okay, is it the only string? Is it the only string? I mean 0, 0. How about this? How about 0, 1, 0? If I apply H over this, what is going to be the result? The result is going to be AB, epsilon, AB, right? Which at the end you are going to have AB, AB. So this is also going to be a valid string. This is also going to be a string in sigma star, which is the image of AB, AB. I mean, which actually the image of that is going to be AB, AB. How about this one? 1, 0, 0. You can see that the result of applying H over this again is going to be AB, AB. How about this one? 0, 0, 1. The result of that again is going to be AB, AB. So basically, it's just like because of 1 will be mapped to epsilon, you can have any number of 1s in your binary string. But the only actually constraint that you have is going to be W should be all those strings that have 2 number of zeros and any number of 1s. And those 1s can be actually applied anywhere, right? So all of the strings in this form will be mapped to AB. So at the end, if I apply the inverse of this homomorphism over this language, although this one is not going to map to anything, but this one is going to map to many binary strings, all those binary strings that will be represented in this way, or those strings that has exactly 2 number of zeros. Okay, so now you can see that why I said inverse homomorphism is kind of, sometimes it can be really confusing. It is an interesting operator. And basically you can see that this is a regular language. Definitely it is a regular language. The reason is it is just 2 strings. Any finite number of strings definitely can be represented using a finite state machine. So this is regular, and the reverse of that is also going to be regular. And it is regular, you can see that I can just basically represent it using this regular expression that I have written. Okay, so now let's back to our theorem. The thing is, we wanted to prove that if I have a homomorphism, if I have a regular language, if I apply the inverse of that homomorphism over the regular language, the result is going to be another regular language. And the proof for this one is also interesting. The thing is, if your language is regular, you can create a deterministic finite state for that, right? I wanted to show you that based on that, I can actually create a deterministic finite state for the H minus 1L when you apply the inverse homomorphism over L. And this is also very interesting, actually, constructive proof. Just assume you have the DFA for L. I wanted to create another DFA for the reverse homomorphism of H over L. So this new DFA that I'm going to create is going to have exactly the same set of states, the same starting state, the same final state. Okay, so everything basically are the same, only the transitions are going to be different. I'm going to update the transitions in the new DFA so that so it's just like in the original DFA that you have, you try to follow for each for each symbol in this new DFA, for each symbol A, I wanted to try and check that what would happen if I start from P and if I follow H of A in the original DFA. Just follow that and just add a transition for all of those cases. So basically the only thing that I'm going to do is this one. Let me show it to you through an example that would actually clarify everything. Okay, so let's just assume that I have this homomorphism, okay, and I have a DFA represented using I have a language represented using this DFA. Because that language is represented using this DFA, that's going to be a regular language, of course, right? I'm going to create, it's going to be a language L. I'm going to create another DFA when you apply the reverse of this homomorphism over L. So how to create a DFA for that? As I said, all the states are going to be the same. The same starting state, the same set of states, so Q0, Q2, and Q1. And the same final states. So this one is going to be final state as well. I just need to update the transitions. What I'm going to do here is that, okay, so in this DFA, what is going to be the alphabet? The alphabet is going to be sigma here. Note that the alphabet here is going to be that phi. Okay, the alphabet is phi. That's going to be AB. the alphabet here is going to be 0, 1, binary alphabet. Now I wanted to see that, for example, what would happen for the transition of 0. What's going to be the transition of 0 over Q0? What's going to be the transition of 0 over Q1 over Q2? So this is the answer. This is the questions that I have. Then I will actually look for 1. So I'm going to actually find the answer here. What I will do here is that I will just check the homomorphism and say that, okay, I'm interested in 0. Okay, what would happen is that the inverse of AB will be 0. Okay, so I need to just check that what would happen for AB if I am at Q0, and if I see a string like AB, where I'm going to end up. So this one, Q0 and AB, where I'm going to end up. Whatever is the answer there, that's going to be the answer for this one. If you start from Q0, if you follow AB, you reach to Q1. So the answer here is going to be Q1. From Q0, with seeing a 0, you should reach to Q1. You see that it's just, the reverse of this mapping, where by seeing AB, you will end up starting from Q0, where you will actually end up here by seeing a 0. It's just, I just follow the definition of this. So for 0, I just need to follow AB here. So I just, for Q1, where you are going to end up, if you are at Q1 and if you see AB, you are going to go with here with A, and then you come back to Q1. So a transition over 0 is just coming back to Q1. How about Q2? By seeing an A, by seeing a B, you are going to Q1. So another transition here from Q0 to Q1. So this is going to be the result. All the transitions of zeros for all the states. Okay? Do the same for 1. Okay, so again, for 1, what I need to check here is that what is the result of the homomorphism over 1? That's going to be epsilon. What does that mean? It basically means that here, if I wanted to check the transitions of 1, I should check that what would happen if I have at any states in these finite states and I see an epsilon. Actually, the answer is simple, that you are going to stay at that states, right? If you are at Q0 by seeing an epsilon, you will be at Q0. So if you are at Q0 by seeing a 1, you will stay at Q0. If you are at Q2 by seeing a 1, you will stay. And if you are at Q1 by seeing a 1, you will stay. That is going to be the result. Here is the final result. This is going to be a DFA for the when you are applying the reverse homomorphism of this homomorphism over this DFA. That's going to be the actual DFA for that. Here is actually another interesting example. Here I just actually didn't go to the DFAs, but this one I just actually found it very interesting. Just assume that I have again an alphabet sigma, a binary alphabet, another alphabet phi, which is going to be all the strings over A and B. And I have a language, you can see that L has been defined over phi. This is going to be represented using a regular expression here. That's going to be all the combinations of double A and a single B. This is a union, and then you apply the killing closure over that. And this is the homomorphism that we defined. I just actually updated the homomorphism. I am actually working on a different homomorphism. This homomorphism will map 0 to AB, and will map 1 to BA. Okay, now let's just answer these questions here. So based on that homomorphism, what will be the result of reverse homomorphism over BA-AB? If you check the definition of the homomorphism, string homomorphism that I have here, BA-AB, you can actually just say that this part will be, by reversing that, this part is going to be 1, right? And this part is going to be 0. Right? So this one is going to be 1, 0. The answer of this one. How about this one? If I apply this reverse homomorphism over this string, it's just like this one will be mapped to, just the reverse of that is going to be 0. This one is going to be 0, and this one will be 1. So the result here is going to be 0, 0, 1. How about this one? If I apply the reverse of the homomorphism over a string like AA, what's going to be the result? Is there any binary string that by applying the homomorphism over that binary string, the result will be AA? So the answer, the question here is that I am looking for a W that if you apply H over W, the result will be AA. So what is that W? So when you are looking at the definition of the homomorphism, you can see that it's not possible to generate double A. No binary strings will generate double A. So the answer here is that it's not defined. How about single B? Can you find any binary string that if you applied the homomorphism here over that binary string, the result will be B? The answer is no. It's not possible to find any binary string that you apply this homomorphism over it and it actually mapped to only a single B. Okay, so now that you actually answered these questions, that those are just a single strings. Now I wanted to actually, I'm interested in defining the inverse homomorphism of L. That is L. So let me actually just, because it's a little bit tricky, let me just look at L. What is L? L is going to be all the strings that has been created by arbitrary concatenation of double A and double B. Double A and single B. So for example, all these strings are going to be in A. A is in L. All of these are going to be in L. This is going to be a part of L. B is a part of L, right? B is a part of L. For example, this one is a part of L, right? And so on. And all those strings, like, for example, B, A, B is also a part of L. Okay, let me just double check. Is this a string a part of L? A, B, A, B, B, A. This is not a part of L, right? Because it's not possible to generate this string by just, a double A or a single B. It's not possible to get this string. Okay, here I have actually, I just wanted to give you a sense that what is L and what would happen if I apply the reverse homomorphism over L. So AA is a part of L, but the inverse homomorphism over AA hasn't been defined. We don't have any definition for this. I don't have any definition for B. I don't have any definition for For example, even this one, A, B. I don't have any definition for this one, right? There is no binary strings that if you apply the homomorphism over that, the result is going to be A, B. The only strings, basically the only strings that can be mapped back here are these type of strings. So this one will be actually mapped, resulted at 1, 0, right? The result of this one, if you apply the homomorphism, the reverse homomorphism here, B, A, B. The result will be 0, 1. This one can be actually mapped. But all of the others here cannot be mapped. If you have only A, if you have only B, all of those are going to be a part of L, right? For example, AA, any number of double A will be a part of, so I should actually just represent it as a subset. This is going to be a part of L, but I don't have any definition for in the reverse homomorphism for this. I don't have any definition for this one, for all the strings which are only B for L as well. They cannot actually mapped using the inverse homomorphism here. The only strings that can be mapped in the inverse homomorphisms are those strings which are in this form. B, A, B. Okay, this one, or for example, you know, all the killing closure properties, all the killing closure of this one, all the just the combination of this string. Only these type of strings can be mapped back using the inverse of this homomorphism. And the reason is just because this definition forced you to only have the binary string that can be actually mapped to these ones. So based on this, the result of the reverse of L is going to be, you know, that this one is going to be converted to 0, 1, and so when you actually apply the star over that, this is going to be the result. So the reverse homomorphism over L is going to be, did I write it as 0, 1? Sorry, it should be actually 1, 0. So let me actually just update this one. This should be 1, 0. This should be 1, 0. Okay, so the result of the reverse, applying the reverse homomorphism over L, is going to be only 1, 0 star. There are some other strings in L, but the thing is the reverse homomorphism hasn't been defined for them. So they are all gone when you are applying the reverse homomorphism over L. And the result is going to be only the binary strings in this form. Okay, so I'm going to finish this lecture. I think we have been talking for a long time in this one. This is going to be a long lecture. This is going to cover section 2 of chapter 4. So just make sure that you do the exercises as well. I will try to post some more examples of how the closure properties can be used to prove that a language is a regular language. Not the reverse of that. You can just use the closure properties to prove that a language is a regular language, basically.